Hello all and welcome to the Introduction to CFD course by Mediocre Tasker. Today we are going to discuss lecture 2, which is setting up a CFD simulation. So what is setting up of a simulation, especially a CFD one? Now setting up simulation involves three parts, which is basically pre-processing, solving the equations, and post-processing. In pre-processing, we first set up the geometry and establish the input, output, and the boundary conditions on the geometry, and then do the meshing on the geometry. So, for example, over here, I considered a geometry, uh, which you can call ABCD, and I am interested in simulating a cylinder which is yellow in color over here. I have the input conditions of 10 meter per second on the left, denoted by the blue arrows, and the output of 0 Pascal, or the absolute pressure is almost 0. That means it's almost equal to the atmospheric pressure on the outside, so there is no what do you call difference of pressure. And if you observe over here, the walls of AB and CD are actually impose the wall conditions. There are a lot of conditions to impose if you want, like slip, no slip, or wall, periodic boundary conditions. So I have imposed the wall. So here I am demonstrating an example which is imposing the wall such that the gradient of temperature, velocity, and pressure comes to 0 at this point throughout the whole wall. Now we define the geometry and the input, output, and the boundary conditions. So this is over here a typical mesh. So this is a basic structured mesh over here, which you can generate using meshing softwares like GMSH or ANSYS or any other software. Now, before doing the meshing, it's important to know some basics about the meshing, such as surface mesh and volume mesh. Surface mesh, that means the mesh which is applied on the surface. If you look at a 3D volume, 3D object, in the real time cases, most of the simulations are done on a 3D cases. So you have a surface and also the volume imbibed inside that surface. So the surface elements are mostly triangles and quadrilaterals, while the volume mesh, which is the hexahedron, tetrahedron, prism, and involves those sort of elements. So as you can see over here, if you can simulate a cylinder which is a finite cylinder, which I meant to say was like the cylinder has volume and also a surface. Then the surface over here you can see is either made up of a surface mesh of triangles, or it is made up of six elements, which is a hexahedron or something like that. Uh, Now, when we look about the volume mesh, the volume mesh involves a hexahedron, a tetrahedron, or a pyramid or prism. As you can see, a classical example over here from the Google, which is a surface mesh on the outside and volume mesh on the inside, which is well knitted or like well patched. So when you look into ANSYS and all that detailed descriptions, you would be getting to know from the ANSYS documentation how actually a surface mesh and the volume mesh and how meshing tool works. Now, since we discussed about the pre-processing, it's important to see how a numerical method is applied on the solver before the solving sets up. So we have like three different numerical methods primarily, and also fourth one which is pseudo spectral but which is not widely studied and only studied in the research part. So the finite difference, finite volume, and the finite element are the famous numerical methods which are being studied in the CFD community. And so the basic principle is that the finite difference method, the finite difference method utilizes the Taylor's approximation from the partial differential equations. For example, here I am considering a one-dimensional heat equation, as you can see from the equation over here. So if it is when assumed in the form of a Taylor's approximation and written according to the stencil notes over here. This can be formulated as such based upon the first principle derivative or Taylor's approximation. So here's a small demonstration. So the same geometry and the same mesh which you earlier looked upon. So basically, if we apply the finite difference principle over here, as you can see over here, uh, if j is taken to be the space and n is taken to be the time step, at this particular time step of n we advance through space, and for going through the next time step we go for n plus 1 and at the same location of space, and for the next time step of n plus 2 we advance, we are in the space of j minus 1, j and j plus 1. So since this is not a one-dimensional case, this is a two-dimensional case, I should be having here also I and j. I involves the dimension in the x and j involve the dimension in y. I'm very sorry for that, since it can lead to confusion over here, but it's what I meant to say was here, like the clear advancement of time and space, as you can see over here. So that is what I want to say here, but I am very sorry for that, because you need to here use uh, two stand we have two spaces over here which is like x and y, so you need to be using j and I for advancement in x and y direction, with also the advancement of time which is n. So this is the principle behind the finite difference method. And if you look into the finite volume method, the principle involves the conservation of energy, which is the flux entered into a finite volume cell is equal to flux exited, and also the flux created inside a cell if there is any source term. So for example, if you look over the cell here, uh, the cell in a finite volume may be considered something like this. In a 2D or a 3D case, maybe consider a 2D case, and all the values which are present at these nodes on the corners or on the edges store their value at the center, which is called as a node. So for example, the values of pressure or velocity, whichever is present at this point in a finite volume cell, stores their value at the node at the center. So this is one of the basic principle. And if you observe over here, this is one finite volume cell, and this is the second one, and this is the third one. So as I mentioned earlier, the values of scalar or any vector or any transport variable such as pressure or velocity is stored at the cell node which is at the center. So for the W finite volume cell and for the E cell, the values are at the center. And if I want to know the value of any pressure or velocity or any scalar variable at this point, I need to write up the equations and in a discretized form. So this is an example which I have taken from this famous book called Weersteeg and Malala Shekhara. Now, as you can see over here, this is a set of 5 nodes uh, for the one-dimensional heat equation, and the equations are written over here as something as 4.14, where it involves the coefficient of thermal expansion, the temperatures at that particular finite volume at that node, which are like Tp, Tw and Te, and also the area of the finite element with the distance to the nodes. So upon writing the equation over here for this element and also continuing to write for all the elements, we achieve a discretized equation, we achieve a set of discretized equations in algebraic form. So that is the principle over here. Now writing up the partial differential equations and converting them into algebraic equations, and from them iterating them until we achieve convergence, is the principle for the solver, which we use it in all the set of numerical methods such as finite difference, volume and element. So I hope I'm making sense and I'm clear. Now if I jump into the finite element, which is also a conservation of energy principle, but it involves the weak formulation, shape and weights. So here we do something called as a strong to weak formulation. That means the partial differential equation is written in the weak form based upon the shape function. As you can see over here, if this is a one-dimensional heat equation, this is transformed into a weak form of the one-dimensional heat equation by integrating with the shapes, uh, and then assuming the shape function and the weight function. So for example, if I wanted to focus more, or the area of interest is this part over here, then I discretize this part more. So as you can see over here, since the width of this part is less compared to this one, and I could give a greater shape, greater weightage for the shape function over here if I'm interested. So that is how it works for the finite element method. And as I mentioned earlier, the solver, the basic ideology or the basic functioning of a solver is that we write the governing equations for the domain, as you can see over here, and also in the finite difference and the finite volume methods. And sorry, and also we convert the resulting integral equations into algebraic ones, as I mentioned in the finite volume one, and we integrate it throughout the domain by the iterative method, which may be Gauss-Seidel or Gauss-Jordan or any other iterative methods which have their particular pros and cons, until we attain the convergence. So I hope I'm clear. So after the solver or the solving part is done, we move upon to the post processing. The post processing is one of the key part to analyze plots or fields or any animations. For example, for that same heat equation or the two-dimensional heat equation, I have got these images from the Google. So if you can analyze what's happening over here, you have the temperature at the bottom, and as you can see through its conduction, I do not know exactly where I got this source from. I just got this from Google, but by looking upon the basic plot, I can say that there's a lot of temperature or heat source over here, and as it moves upon, it reduces based upon the scale from here. So there might be a source of heating, or a heat is being emitted from these directions. So the temperature around this profile is less compared to this one. And also when you perform any numerical simulation, you compare the exact and the numerical ones, and this figure over here is one such case where you see the difference between the the exact and the trial solutions. So which is almost I don't know, like which is almost of no difference. So these are some random examples of what you can do in the post processing, and saying that your numerical solution has attained some validation based upon this image over here. uh, if you set up the geometry and the meshing very accurately, that means there are no corner edges and they're properly patched, and the meshing is done very fine, and it has attained a grid independency, almost 50 to 60% of your solution accuracy is determined from those part itself. The later is how you solve the simulation and how you invert the matrices and writing of them and post processing them. So half of the work is done if your geometry and the mesh is very fine. So that is how a setting up of a simulation in any CFD tool which you are working on. So that's it for today, and I hope you had a good basic on how to set up a simulation, and I thank you, and I hope you have a wonderful day. And in the following, we discuss about the continuity and the momentum equation. I'm sorry, and yeah, thank you.